I'm Ksenia Khabarova from Lebedev Physical Institute of Russian Academy of Science, and today I'm going to tell you about cold atoms and ions and traps. And we can consider this very nice quantum technology like miracle. So let's start. What we are going to talk about today. First question is how to catch an atom or ion. Second is how to cool down atoms and ions in the trap and why. And the last but not least, what for we need these trapped cold particles. Okay, let's start from the one easy problem. So we know from the course of electricity that ion is a particle with a charge. So it's some atom which is lack of one or some number of electrons. And to understand how to catch it, we can add some knowledge about the Coulomb interaction. So the charged particles will feel in other charged particles, and thus we can influence it. And just to have a feeling, we need to understand what is the size of an atom or size of an ion. So the size is approximately on the order of 10 to minus 10 meters. And if we compare the ion with an apple, then we can compare the apple with the Earth. So this comparison will be more or less correct. So, but we know from the in-show theorem that the collection of point charges cannot be maintained in stable stationary equilibrium configuration solely by the electrostatic interactions of charges. It means that we cannot just take some charged part of metal and surround the ion with such metal parts and make it to be trapped, right? And this somehow confined in the space. It doesn't work. But we can use alternating electric fields, and we have a very nice picture how it works even in the mechanical model. Let's have a look on this video. So this is a table, it rotates, and if it's stable, so without rotation, the ball will fall down from this table. However, if it starts to rotate, you can see from this video that the ball will be trapped in such a configuration. And if we talk about the alternating electric fields, we can consider it the same way. So we have, for example, 4 rods. 2 of them will be grounded, and 2 other will be with radio frequency electric field, which will alternate from the minus amplitude to the plus amplitude. And it will be very similar to our rotating table. And the ion, which we put in such alternating field, will feel the same like a ball on this rotating table, and it will be catched. Okay, so we understand that to catch an ion, we need such alternating electric fields, and how to make it. There are some different possible solutions. First, ion traps can be 3D or surface traps. So we can take, like in previous slide, we can take just 4 rods, or maybe not rods, but blades, and smartly applying electric fields, we can catch an ion in such a trap. And it means that we use 3D trap. Otherwise, we can use surface trap, and let's have a look on another video. So as you can see, the ion flies under the surface trap, and one can control its position with electric fields. We can apply different types of electric fields to make the ions move and go closer to each other. Then we can do something with them with a laser, for example, and then again control their position. So this is very high technology. It's already has development for many years. It's close to microelectronics. Okay, what we need, what we want to have. We want to have such a nice string of ions, and to crystalline such an ensemble, we need to cool down the ions to the temperature of very close to absolute zero. However, we are smart people. We have to ask ourselves one very important question. What is the temperature of a single ion? When we talk about temperature in our usual life, we talk about the thermometer, which can be put somewhere and we can read the number on it, and then we know the temperature of the environment, of a body, of something, of some liquid, and so on. And when we have only one particle, what do we mean when we talk about the temperature? And actually, it's a very tricky question, because from the point of view of thermodynamics, the concept of temperature, strictly speaking, is applicable only for a large number of particles which are already in a thermal equilibrium. Otherwise, we cannot talk about temperature. Another, maybe you heard about it, if the ensemble is in Maxwell distribution, so if the motion of these particles in the ensemble can be described with Maxwell distribution, then we can talk about the temperature, because the temperature very closely connected to the entropy. And the entropy is something about thermal dynamics, thermal motion. So it means that if we talk about one single particle, we have to distinguish which motion of its particle depends on the thermal kinetic energy and which one is not the thermal kinetic energy. For understanding, let's consider this very nice picture about supersonic flow of particles. You know, it's particles which go in one direction with a very high velocity. But actually, in this case, if you have a look on this picture, on the upper part, then you can see the divergence of this flow is very, very low. And it means that the temperature of these particles is really low. Also, the velocity of the directed motion is very high. So when we talk about the particle, we can, let's say, use the term of temperature to describe the thermal motion of this particle. If we have an ion in a trap, then it's already trapped, so it has no directional motion. Then we can consider temperature like, let's say, thermal kinetic energy, which we can divide in two parts according to the axis. Okay, I've written down here on this slide some constants which we need to understand what we can use when we cool down the ion with a laser. So we need Planck constant, speed of light, frequency, energy of the particle, and momentum. So radiation, we can consider radiation as a flow of particles, photons. And each photon has momentum, energy, and frequency or wavelength, which is almost the same. So let's have a look on this. Again, we know from the school the Bohr model of atom. So in this model, each atom has an electron, and this electron can have only certain energy values. And this energy quantized. What does it mean? So if we have a photon with some energy and it goes to the atom can absorb this photon if the energy of the photon coincides with the difference of energy levels. And thus, atom has this additional energy, and the electron goes from the lower energy state to a high energy state. So it increases the energy of the orbits. If the excited state decays, then the photon takes the extra energy out of the atom, and we have a photon with the energy of difference between these energy states, and again an atom with lower energy. So let's have a look on this example. We have a man on a cart which sits on the cart, and the cart moves. And we have a flow of apples, which this man catches. So the man catches apples flying towards him and then scatters them in some directions, in all directions, without any preferable direction, let's say. And the velocity of the atom is again the same when the man catches that. So what it means that in every act of catching an apple, a man gets some energy and momentum, right? And we know that the difference of the momentum before the act of catching apple and after it will be different. So the atom, or not atom, our apple, which man catches, will change the momentum of the man on the card. And I've written it here on this very simple equations. So if we consider the velocity of the apple to be approximately 1 meter per second and mass of the man about 100 kilos and the mass of the apple about 100 grams and the card has a velocity of 1 meter per second, then every act of catching an apple will change the momentum of the card by 1,000 of meter per second. So to stop the card, man has to catch at least 1,000 of apples. And again, it is very important that when the man has this apple, he throw it away in some random direction. And then after averaging over all directions, the changing in the momentum by these acts will be 0. So iron does the same. It scatters millions of photons per second in this act. So just let's have a look further. So if we have an ion which has some motion and a photon, we have, for example, two contrary cases. So in the first upper part of the picture, we can see that the photon goes towards the atom or ion, which has some velocity. And then in the coordinate system of a laboratory, the frequency of a photon will be lower than the frequency which will see the atom. And then this energy may be enough to excite an atom or ion, which is the same. And then the excited state will decay. Again, it will be some random direction. So in averaging, it will be 0. Or maybe another case when the photon goes after the ion, and then the energy of this photon from the point of view of atom is not enough to excite it to the upper state, and then ion just doesn't see any photon and nothing happens. And again, we have to remember this is a Doppler effect. So when we hear the car which goes towards us, the sound has the higher frequency. When the car goes from us further and further, the frequency will go lower and lower. So the Doppler effect, and it will also work out for the atom and the light, so the photons. Okay, just a little bit of formulas. Laser cooling. The same thing happens with an atom or ion when we have two-level atomic system, like we see on this small video, and optical field. Atom could be in one of two states. It can be either in a ground state or an excited state. And then this excited state somehow decays after some time. It's not important at the moment. So when the atom absorbs the photon, and you can see when atom goes towards the photon starts to be more blue, and if it goes further from the photon, the frequency of the photon for atoms should become red. So we again have to remember about two fundamental laws: energy conservation and momentum conservation. And here we write it down. Okay, we have to remember about the difference between energy states, excited and then ground states, and Doppler effect and recoil energy, which always have to be there because the photon has a momentum, so it will be recoil. And two processes we can consider is absorption and radiation. In the end, I didn't want to stop here on the very complicated stuff, but we have some limit for the cooling. So we cannot cool down the atom to the absolute zero because we always have this equilibrium between Doppler effect, which we can control, and the recoil energy, which we cannot do anything with it. So there is some very very good defined thermal limit for the exactly this transition, which we can use to cool down an atom. Okay, so we were talking about ions because ions allow us to use column interaction to first trap them in the ion trap and then cool down with a laser using the Doppler effect. So the next question, how to trap an ion? So first of all, we need a source of ions, and it may be atomic oven. Talking about ions, it's the same second question, but it's a little bit easier because ions we can produce inside the trap just if we have the same atomic flow. So atomic oven, we need to evaporate the atoms and have a flow of atoms. And of course, these atoms, because we need to heat the piece of metal, for example, it will be with a very high speed, right? So first we have somehow to slow them down because no existing today traps don't allow us to catch very, very high speed atoms. So first we need to slow them down. We again use the Doppler effect, which we already remember. And another one which we need is the Zeeman effect. So again, not going far from the school course to some very complicated atomic physics, we just have to know, believe me, that the resonance of the atom is rather narrow. And when we have a flow of atoms and a laser beam which slowed it down due to the Doppler effect, after several acts of absorption and again radiation, the atom will be a little bit slower than in the beginning, but it will not be in resonance with this laser beam already. So what we need something else, and this is the Zeeman effect. So when we have a magnetic field, the energy in the atom will move. So it will depend on the value of the magnetic field. And then if we are smart enough and we can calculate the Zeeman lower, so it's some combination of, let's say, magnets, which form some gradient of the magnetic field. So it's some magnetic field which will be changed from one point of space to another along the axis of the atomic beam. Then we can make during the process of laser slowing, we can coincide the energy difference between two levels with the rate of the laser cooling. So with this Zeeman slower, we can slow down the whole flow of atoms to the velocities approximately from 1 to 30 meters per second. And it's very good because in this case, we already can trap them in a magneto-optical trap. So this is a little bit too complicated to explain just for the school course. So we just believe in this picture. So the magneto-optical trap consists of 3 pairs of laser light and 2 magnetic coils, which produce the quadratic magnetic field. And it makes the forces which actually kick the atoms to the center of the trap where a magnetic field is 0. And then to the right, we can see very nice cloud of cold atoms, which are just fly inside the vacuum chamber. And it's a number of these atoms, it's millions of them. So what we need, again, of course, it's a very high vacuum and the laser and the magnetic field and to slow down the atoms beforehand. So, okay, again, let's go back to the question of temperature. In this case, we have an ensemble of atoms. Can we actually judge about the temperature? And how we can judge about the temperature? Again, we have nothing to put there inside the vacuum chamber to measure it, because anyway, we are talking not about the temperature in our usual point of view. So, for example, this is the strontium atoms, which are catched into the trap. And to estimate the temperature, we again look at the motion. And to consider it, to understand it, we just let the cloud to fall down. This is the picture. So this is a photo of the cloud, how it falls down and actually ballistically expand. So the ballistic expansion gives us the result which we can judge about the temperature. And on this small video, you can see how it actually goes down. And this falling we do not take into account because it's directional motion due to the gravitational field. And the only thing which we are interested in is the expansion. So the expansion gives us the judge about the temperature. So this is a very cold atoms, which you can see, because the temperature is about 35 microkelvins. It's very, very cold atoms. Okay, when we have such a low temperature, we can do the next step and trap atoms into optical lattice. Optical lattice is a standing wave. You have two lasers, which just go towards each other, and we have the standing wave, and we can catch the atom, every atom, in some minimum of this light, of the standing wave. Why? Again, it's a little bit too complicated question, but believe me, we can. And thus we have a very nice number of, like, say, the pancakes of atoms, which are located in a very good oriented way. Okay, so the last thing which I wanted to tell you about is what for we need all these cold particles. So we understand that we can trap them, we can cool them down, we can cool them down very low to very low temperatures. We can put some optical lattice with them. And what for? What is the reason? First of all, because it's a beautiful physics. One of the very beautiful experiments which were made last 50 years, it's a Bose-Einstein condensate, which was demonstrated even in space. What it means, when we have the thermal atoms to the left, and we just have a look how it expands, so it's isotropic expansion. And the Bose-Einstein condensate, which we can produce if we go to very, very low temperatures with a very, very high density of the atoms, and of course it should be bosons. Then they can occupy the same energy level, and then we can see that because of the anisotropic confinement in the magnetic trap, it will expand differently. It will be not the isotropic expansion. So what for we need the Bose-Einstein condensate? It's really difficult to say because some practical applications they were not found at the moment. But it's first of all, it's interesting. Second, it's beautiful, and it illustrates really that the quantum mechanics works. Okay, what else? Operating with the cold atoms in such object like optical lattice, we have an ability to make an array of atoms and collect them in any picture we want. What for? For example, it can be a quantum simulator or quantum sensor or quantum computer. Next, And it's a very important application, because with cold atoms and ions we can make an optical atomic clock. And the optical atomic clock is the most accurate and stable device in the world today. So the accuracy and stability of such clock reached already 10 to minus 18 in relative units. So what it means that these such clocks will have the error of 1 second during the time more than life of our universe. So it's really extremely accurate device. And on this picture you can see what it consists of. So we need, of course, atoms, like here in the lattice, for example, it's a neutral atoms. We need a laser to ask the atoms about the frequency of their transition inside it. So the transition should be really very strictly forbidden to make the possibility of the excitation of this transition only when the laser is very, very accurately coincide with this transition. And we need something like extra lasers, some electronics, and so on. And of course, the laser should be stable. So the spectral line width of the laser should be very, very narrow. So our atoms in the vacuum chamber should be as isolated as possible from the environment. They should not feel any thermal radiation, any magnetic field, any electric field. Everything should be controlled. And then we have the same, it's a big amount of the same particles, which are the same here, the same in Africa, the same in Brazil, and everywhere. It will be everywhere the same particles. And then when we ask them, so the main question of the clock is comparison. Just like comparison of the clocks is the basement of the timekeeping. So we can compare these clocks from one lab to another, and then we see that how we can control everything around us. Like this optical clock, they can be used for many fundamental and practical applications. The most bright of them is navigation. So if you have the GLONASS or GPS or Baidu or anything else with solid space apparatus, and they have some clocks on it, and we have the clocks on the Earth, and we can compare them, and then we can very accurately measure and define our location on the Earth. Okay, what else? Quantum computer. So atoms and ions today are considered as the basement for the quantum computing. And what lays down in this question is that the quantum computer is somehow very similar to usual computer, but the encoding of the information is different. In the regular computer, we just use zeros and ones, like 2 bits, to encode the information, and in the quantum computer we use so-called qubits when we encode the information in the state of the quantum particles. And of course we can use it, we can do it only if we have a very well-defined quantum particles. Talking about ions, we have a string which do not move, and we can address every ion individually. And of course, it's talking about the future. The ion quantum computer is one of the most promising over all the platforms are already existing. And the most powerful quantum computer today is based on the cold ions in ion traps. What else? Let's have a look here. We can measure gravitational potential using the optical clock, because the atoms are very, very sensitive. And if we isolate them from the environment, then we can ask them about the frequency of their transitions, depending on in what gravitational potential it's located. And it allows us to build a map of the gravitational potential and, for example, make a map of geoid. Last, which I would like to maybe, not last, but very interesting part, is the search for dark matter and energy. You know, there is a problem that from the very beginning, we cannot understand why the universe consists only of 5% of visible matter and where everything else. We cannot find it yet, but we know that there is a lot of dark matter and enormous part of dark energy, but we cannot feel it. Maybe cold atoms and ions will help us to do it. And last, which I wanted to just to mention, is the quantum sensors. If you have very cold atom, then you can control all these states of the energy, and you can excite it in a very, very high energy level. And in this state, it will be very sensitive to many other environmental fields, like electric fields, like magnetic fields. So you can use very cold particles like a sensor with a very, very high accuracy. And of course, there are many others. Thank you.